Okay, good morning, everyone. Let's get started. As always, orienting relative to the assignments. Undergrads, you're tackling assignment 4 this week, which is sensors, giving your robot the ability to sense some aspect of the virtual world around itself. So far, for the undergrad, you've been working in PyBullet, which is exactly what we're going to talk about in lecture 6 today, the physics engine itself. A physics engine is not necessarily a robotics simulator. There's other stuff you often need to add to a physics engine to get it to be able to create a robot for you. In assignment 4, you're going to be adding some of that, which is sensors. Sensors are not an atomic building block of physical simulation. It's something you're going to be adding on top of PyBullet. And in order to help you with that, you're going to be using PyroSim, which is a little bit of code that I wrote. That's a little bit like a wrapper. So again, all of these assignments are like Russian nesting dolls. We have the kernel of PyBullet, the physics engine itself. Around PyBullet is PyroSim, a little bit of code that I wrote that makes it easier for you to create robots in the physics engine, and you're going to be adding some of those elements this week, which are sensors. Does that help? Less confusing, more confusing?
Grads, I assume that later assigned, not due today.
Oh gosh. Assigned, you want it assigned or due? Maybe assigned. Okay, good catch. Good catch. Just making sure you're awake this morning. Misspelled. Okay, you know what I mean. Better? Now I'm really confused.
5 and 6. No.
What did I do? Now I've made it worse.
So AO5 and AO6 were due yesterday.
They were due. Thank you. That looks better. Okay. Grads, you're tackling AO7 and AO8, which is assigned today and due next week. 7 and 8 will complete the virtual robot for you. You'll be adding neurons and synapses to your robot, which connect the sensors and sensor neurons to the motor neurons and the motors themselves. We talked about neural networks last week. Neural networks for a robot transform incoming sensory information into action. They change sensation into action. You'll be finishing your robot in assignment 8. In assignment 9, you'll wrap an evolutionary algorithm around your virtual robot to start evolving your robot to do something you want it to do. And in the 10th and the final assignment, we'll throw away this minimal 3-link, 2-joint robot that you've been working with so far and replace it with something a little bit more interesting. Okay, everyone oriented, more or less? Okay, so back to the tools of the trade, which we're talking about this week and into this week. We're going to finish lecture 5 in a moment, evolutionary algorithms. Just to bring you back up to speed, in a lecture 5 here, we're walking through a series of search algorithms, search heuristics. They are all moving through the space of all possible, in your case, all possible robots. You can think of these evolutionary algorithms as moving through a high-dimensional space where all of the quote-unquote horizontal dimensions in this space correspond to the genotype or some instructions that make up the robot, and the height of each of those points is the fitness or how good or how poorly the robot does at whatever you want it to do. As we marched our way through these evolutionary algorithms, sorry, let me see if I can find it again. We did not quite finish lecture 5, evolutionary algorithms. As we were marching through these algorithms, we started with very simple algorithms, which had the benefit of being very simple, but the drawback of being what? Why not just stick with an evolutionary algorithm, a simple search algorithm?
They get stuck in local optima pretty easily.
They get stuck in local optima pretty easily. This high-dimensional fitness landscape idea that we introduced last time, there are a lot of local peaks. Search algorithms tend to get stuck on them, including state-of-the-art machine learning algorithms, unless you have an obscene amount of data, it would seem. That's at least where we are in terms of machine learning. Okay, so we and this community that studies evolutionary algorithms continuously is trying to devise cleverer and cleverer evolutionary algorithms in an attempt to reduce the chances of getting stuck on local optima. That was one sort of theme we saw running through all the search algorithms we saw last time. Another aspect that differentiates different evolutionary algorithms is the encoding, the way in which the genetic information is encoded. In everything we saw, last time, everything was encoded as a vector. So the vector is some very crude approximation of our genome or our DNA. Inside each element of that vector are values specifying some aspect of the candidate solution. Imagine a Bratenberg vehicle with a bunch of wires inside. We need to assign weights to all of those wires. Are they excitatory? Are they inhibitory? What's the magnitude of the weight of that synapse? You can think of those as the genes. We ended last time with the evolution strategy, where we sort of broke out of this genetic encoding of simple vectors, and we saw simple 2x(n) matrices, where the second row indicated how fast or how slowly this search algorithm or this evolutionary algorithm moved around these horizontal dimensions of the fitness landscape. Okay, sorry, we didn't end with the evolution strategy. We ended with the last evolutionary algorithm we're going to talk about in this class, and we didn't talk about that evolutionary algorithm itself. We started by motivating this evolutionary algorithm, which we haven't seen yet, with a specific problem that it was designed to solve, and that problem is symbolic regression. You collect a whole bunch of data, like, for example, where there are or aren't algal blooms in the lake. You have this huge spreadsheet with all of this data, and you would like an AI to distill all of this data down, compress it into a function of T equals, T for toxic algal blooms. If the AI is able to write down an equation for you, in theory, armed with this equation, you can start to make predictions for where algal blooms are going to start to appear in the lake. If this function involves terms that have to do with, for example, water temperature or where in the lake these things are occurring, if you can get these measurements. Mallett's Bay seems to be warming up quite a bit at the moment. We plug those values into the right-hand side of the equation, and we get a value back for T, the likelihood that there's going to be a toxic algal bloom in that place in the not-too-distant future. Yeah. This is a notoriously difficult problem to solve, symbolic regression, automatically teaching an AI to distill or compress data down into equations. We started to see the outlines of this evolutionary algorithm last time, where we looked at some cartoon data here, and we started to guess. We started to generate equations that might explain that data. I formulated a bad guess, y equals x, and we can see that this particular equation has high error, therefore low fitness. Someone else suggested a much better equation. It's got different symbolic form. That's the symbolic part of symbolic regression, which explains more of the data, not all of it, so it may not be optimal. So the last evolutionary algorithm we're going to talk about is known as genetic programming. And in genetic programming, we still have a population of candidate solutions. This algorithm still deletes the low fit solution and makes randomly modified copies of the more fit solutions. But now individual candidate solutions in this population are equations. Okay, so we are no longer dealing with a vector of numbers, we're dealing with equations. How do we get genetic programming to encode a population of equations with arbitrary form. We're going to use the tree data structure. And for those of you, those non-computer scientists who have not seen the tree data structure before, don't panic. It's pretty intuitive. We'll go through it now. So at the beginning of genetic programming, like in all the evolutionary algorithms that we've seen, we need to generate a population of random solutions. In genetic programming, it's going to be a population of random equations. How do we do that? The first thing we need is for the human programmer to write down all of the possible operators or transformations that they think may be relevant to the problem. This is usually just simple arithmetic and trigonometric functions. So we're going to throw into our bag of operations here sine, cosine, addition, minus, multiply, divide, and the power function. We're going to assume, and maybe it's a big assumption, we're going to make an assumption that the AI or the genetic programming in this case can cobble together or find a way to build an equation using these operators that will capture whatever's going on in the lake or whatever's going on in our data set that we're interested in. As human programmers with our puny human minds, we often don't know, so we err on the side of caution. You can throw more operators in here if you like. Okay, we're also then going to formulate a bunch of operands, or the operands such as, for example, x, y. In our example here would be we'd throw in n, p, w, b, r, t, all of the terminal nodes or the things that genetic programming should be able to build these equations from. And then we'll also throw in some random floating point numbers, because numbers are also probably going to be a part of the solution. They're going to end up being coefficients for these terms, constants, who knows. It's just stuff. These are Lego bricks that we're making up that the genetic programming is going to start to play with. So far, so good? Okay. All right, here we go. We start running genetic programming. It's got an empty population. It needs a population of random solutions. So it starts with empty slot 1 and takes this bag of operators and operands, shakes it all up, reaches in and pulls one out at random. And in my cartoon example here, P1 or parent 1, it happens to grab the multiply operator. Multiply requires two things to multiply together. So we place multiply at the root of this tree. This is a data structure that you can build in Python or any programming language. We start by placing the multiply here, and multiply needs two other things. So we create two subtrees down here. We create two empty circles that we're going to have to fill. Multiply can't multiply null times null. It's got to multiply actual mathematical things together. So we've got two empty nodes down here. We start with this empty node. We go back to our bag of operators and operands, shake it up, and grab one of them out at random. In this case, GP has grabbed plus. Plus also requires two arguments. So we create two empty circles underneath. We go to this first empty circle, reach back in the bag, shake it up, pull something up. And in this case, we pulled out a random numerical constant. A numerical constant has no arguments associated with it. So we're done. We don't go any deeper into the tree. So far, so good? Okay, we've got an empty circle still here. We've got an empty circle over here. So we just keep repeating this game. We filled this empty circle by reaching into the bag and randomly pulling out x. We reach back into the bag again and randomly pulled out 1.4.
When we reach into the bag, does the bag contain branch nodes and terminal nodes, or is it just...
It contains branch nodes and terminal nodes.
Okay, so
And
it could be an operation that you get back or a number.
it could be an operation or a number or a variable. This is the simplest version of genetic programming. There's more sophisticated versions. There's hundreds of versions of genetic programming. Simplest thing, doesn't matter. You just grab something at random. Okay, so we've done this once and we've created a random equation, which is, so we now have a tree, which is encoding an equation. For the computer scientists in the room, hopefully you should be able to read off from this tree what the equation is.
0.8 plus x
times 1.4. So for the non-computer scientists who have never seen the tree data structure before, we're going to drop down through the tree, and as we do, we're going to write out the equation that's being built as we visit each node in the tree. For our purposes, the exact way that this is done that you just demonstrated, it's not too important. If you're not familiar with trees, you'll have to take it on faith that if you construct a tree by reaching into this bag at random, you can then walk across this tree and write down an algebraic equation, which is, as you said, open bracket 0.8 plus x, close bracket times 1.4. Okay, we keep going. We now have n minus 1 empty slots in the population, so we go to the second empty slot, which is going to be parent 2, and we do the same thing. We keep shaking the bag and we keep pulling stuff out of it. I forgot to say, we keep pulling stuff out of it, and when we're done putting it in the tree, we put it back into the bag. Random choice with replacement. Yeah, you can pull out as many X's as you like, or anything else. Okay, so in this case, I won't go through it, but in this case, GP has generated a second random equation, 0.2 divided by open bracket x plus y closed bracket, which is what we have down here. Okay, you can continue that process and create a population of 100 random equations or 1,000 random equations. It's up to you. Okay. What do we do at that point? Well, like every other evolutionary algorithm that we've seen, that we now have our population of random candidate solutions, we have to assign a fitness value to it. We have a fitness function that computes the fitness of each equation, and we saw how that works already. We have our raw data. The raw data is represented by the dots here. We can plot the equation, this random equation that's been generated by GP, and we compute the residual error, or the error. How far is the equation represented by the thick line from the raw data? The further it is from the raw data, the lower its fitness. The closer it is to the raw data, the higher its fitness. That is the fitness function. All good? Okay. Okay, and then as usual, the genetic programming will select from among that population. It will delete the ones that have lower fitness, that don't explain the data very well, and genetic programming will make randomly modified copies of the survivors to fill all of these recently vacated empty slots. We've seen two different forms of randomly modified copies, ways in which evolutionary algorithms vary the children relative to the parents. What were those variation operators we saw last time? We saw two. Mutation and offspring is the thing that is modified, but what modifies the offspring from the parents? As we're copying the parents to create the child, we don't create an identical copy. We often mutate the child. What other variation operators did we see last time? Crossover. Sometimes we take two parents. Sometimes we take two parents and we grab a bit of genetic material from both parents and put it together in some way to create a child that's different from each parent, but resembles both parents in some way. Okay, in genetic programming, there is both mutation and crossover. Let's start with mutation. Here's the original parent 1 down here. Let's assume that parent 1 survived. Whatever this equation here does a pretty good job of explaining the data. So it survives, and as we're filling in these empty slots, we grab P1 and we start making a copy of this tree. How might you embody mutation? Mutation intuitively is something that makes a local change. Crossover is a little bit of a larger change. We're mixing and matching genetic material from two parents. How might you mutate P1 to produce a mutated offspring of P1?
Replace a random constant or operator with another one.
Replace a random constant or terminal node variable or an operator with another one. Exactly. So I could delete all of P1 and then reach into the bag and pull out operators and operands again at random. But that's a big change, about as big change as you can make. So let's do something a little more localized. So let's pick a node in this tree at random. We've got 5 of them. We choose this one at random, shown in red here. We delete 1.4 that's in there, and then we reach into our bag again. We might try and create a small mutation operator, something that makes a mild change. If we're deleting a constant, maybe we pull another constant out of the bag. Or maybe we add or remove a small value from this constant. We could do that. That's a smaller change. We could make a slightly bigger change by deleting the constant and basically not carrying what was there before. We're just back to an empty circle. And now we reach into the bag again. Maybe we pull out another constant. Maybe we pull out an operator. Maybe we pull out sign. Sign requires just one argument. So we delete 1.4 and we write sign in there. Are we done? Are we done with this mutation operation? What do we need to do? We need to add another terminal node. So we add another empty circle underneath the sign, reach into the bag again, and we've effectively altered this equation. The child equation down here would be 0.8 plus x times sign of whatever we pulled out of the bag. That would be a mutation operator. We're making a local change to the genotype, the blueprint of our candidate solution. Okay. You can see I've already set us up to discuss crossover. Crossover requires 2 parents. So here's P1 and P2. In order to embody crossover, we need to choose a location in parent 1 where we're going to make a cut, and we need to choose a point in parent 2 where we're going to make a cut. In this case, we've chosen to cut P1 here and cut P2 here. What do we do? At each of those crossover points, we separate, we pull off the subtree. In this case, it happens to be just a single node. In this case, it's a 3-node subtree. We've pulled off 2 bits of genetic information from the 2 parents. What do you think we're going to do to finish this up? Given the name of this operation. We take this bit from P2 and we plug it into C1, and we take this bit from P1 and we plug it into C2. If you now visually compare child 1 to parent 1, you can see that this child resembles its parent, at least in part of the equation, in part of its genetic blueprint, but it also is different from P1 over here. It's a little mix of both parents. You might remember when we talked about crossover last time, the whole idea underlying crossover, the reason that Mother Nature invented sex in the first place, is sometimes you bring together the best of both worlds. And in genetic programming, you can kind of see this idea at work explicitly. You can see that we're literally recombining subfunctions within 2 larger functions. Maybe P1 was pretty good at explaining part of the data because it got this part of the equation, the underlying equation, right. And P2 explains some other bit of the data by getting this part of the equation right. And the beneficiary, C1 down here, that gets this good piece from P1 and this good piece from P2 is going to do a much better job at explaining more of the data. Question?
Do we place some sort of limitation on the size of the equations? Or is it just like randomly decided?
Do we place a constraint on the size of the equations? What do you think? Probably yes, because? Why do we need to? What might happen with the algorithm that I've described to you so far? Absolutely. So when genetic programming was invented back in the early 90s, people who coded it up started to notice bloat. These trees started to get very, 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 very large very quickly. And it's still a bit of a problem in this particular field. So you can often just put a cap on the size. But what cap? Assuming there is an equation that can actually, if we have enough data from the lake, if we were actually to run this GP on data from the lake, how complicated is this relationship? I can tell you that algal blooms are not just a function of phosphorus, and they're not just a function of nitrogen. You can actually make a bit of a prediction by taking the ratio between nitrogen and phosphorus. That actually leads to an okay prediction, but not great. There's other equations that are n over p plus, I forget which one here. You can keep adding terms, or not you, genetic programming can start to build bigger and bigger trees that do a better job of predicting. Hard to actually say a priori how big they should go. If you put no size limit on the trees, they start to grow to hundreds or thousands or millions of nodes. Probably not so great. But hard to know a priori what the size should be. Interestingly, in your DNA, there are a lot of parts of the DNA that seem to not code for any function. There seems to be non-functional genetic material in our genome, although it's a very controversial issue. Most biologists have a hard time swallowing the fact that Mother Nature is that inefficient. If there's stuff in your DNA that does nothing, why doesn't Mother Nature get rid of it? That being said, as far as we know, we haven't found a function for a lot of the parts of our genome yet. Maybe it's just a side effect of the way that evolution goes, possibly. For those of you that do a lot of coding, if you go back and look at your old code, what do you often find in your old code? Bugs, yes, agreed, me too. Aside from bugs. A lot of nested if statements. How about commented out code? I don't know about you, but I often write something, I'm like, maybe this is a good idea, maybe it isn't, maybe there's some bugs in it. I'm going to comment, I don't want to delete it, but I'll just comment it out, and I'm sure my future self, who will be smarter, will come back and know what to do with it. I've gone back and looked at code that I wrote years ago, and it's like 90% commented out code. Not necessarily a bad thing to do. Just kind of interesting that when you look across artificial evolution, biological evolution, the way that we write code or create complex, abstract things, there's often non-functional parts in there. Kind of interesting. Okay. All right, so we've talked about symbolic regression. It's an ongoing problem and issue and has very practical usefulness if you can solve it or do it better. Genetic programming was created to evolve equations to do symbolic regression. Genetic programming, the name of this set of evolutionary algorithms, the name itself implies that it's used for other things. If you're evolving populations of trees that encode equations, you can also evolve populations of trees that encode computer programs. That was another original use of genetic programming. Coding is difficult to do by hand. We now have AI that can kind of help us with coding. But back in the 90s, there was this idea of just explaining in a fitness function what you want your code to do, and then evolving computer programs that do a better and better job of instantiating what you want it to do. It's also known as automated program synthesis, kind of an interesting branch of computer science. Okay, what else can you do with genetic programming? Let's do something fun. What is genetic programming doing in this case? It's evolving a picture of Mona Lisa. Okay. Can we be more specific? So it's evolving a picture of Mona Lisa. What do you think the genotype is here? What is the phenotype? What is the fitness function? You're getting a lot of visual hints here. Any ideas? Yep.
Genotype seems like it might just be a bunch of shaded polygons.
The genotype is a bunch of shaded polygons. So imagine a big tree, and at certain points in the tree, there's a node that says this is the beginning of a polygon. And as you go down into that subtree, other nodes encode vertices of the polygon, other nodes encode the color of the polygon, and one other node encodes alpha, which is, for the computer graphics folks, transparency. Larger trees encode more polygons, smaller trees encode smaller polygons. That's the general gist of the genotype. What's the phenotype? It's a rendering of the polygons on top of each other. It's what you're looking at. You're looking at one phenotype after another. You're obviously not looking at abstract data types like trees. That's the genotype underneath that encodes the phenotypes. What do you think the fitness function is? What's the quality of any given tree in the population? It's the difference between the phenotype and the actual Mona Lisa. Can we be a little bit more specific? We started with trees, the genotype. We went to polygons, which is the phenotype. Mona Lisa was not originally painted with polygons.
Maybe color.
Color of
Color of any given pixels to the original.
any given pixel. So now that we have the polygons, we pull out the colors of the actual pixels and compare them against the corresponding pixels in the Mona Lisa, and the overall error or distance between these two sets of colored pixels, that's fitness. The lower the distance, the higher the fitness. So you've got the genotype, phenotype, and fitness function. Again, just given the fact that this particular genetic programming run has a visual representation, what can you tell me about the evolutionary dynamics here? What's going on over evolutionary time, which is what we're seeing in this video?
It gets like a really abstract representation of the Mona Lisa pretty quickly, but then the details of it seem pretty difficult.
The details seem pretty, it gets sort of the broad outlines, literally, near the beginning, and then it seems to struggle with the details. Why, do you think?
I would say the algorithm is pretty large polygons, so it's hard to get the smaller details in.
Actually, it can make arbitrarily small polygons. Doesn't seem to be doing that. Why?
Would those be in a smaller minima or maximum? It's getting stuck in a vertical one.
Exactly, right? So hard to think about why progress starts to slow down here. This is what the fitness landscape thought experiment is for, right? You can think of genetic programming here as jumping around horizontally in the fitness landscape, and it very quickly climbs some local slopes where it gets a good abstract approximation of the Mona Lisa, and then maybe a mutation or crossover does try and add a smaller polygon by chance. What's the chance that that smaller polygon is going to capture that small random polygon, randomly sized, shaped, and placed? What's the chance that it's going to capture some detail of the actual Mona Lisa? That probability is very low and goes lower and lower as things proceed, right? There is a small polygon that could be created that with one or maybe two polygons would beautifully capture some detail of the Mona Lisa. But the fact that the evolutionary algorithm is going to stumble across it by chance is low. At any point in this video, it's kind of sitting on a hill, and any step genetic programming takes in a horizontal position makes things worse, not better. Yeah. Okay, that concludes our discussions about evolutionary algorithms. Any questions or comments you want to make before we move on? Okay, switching gears, we're going to talk about the third and final main tool of the trade in evolutionary robotics, physical simulation. Luckily, at this point, you all have some experience with physics engines. You already hopefully know how finicky and temperamental they can be. They're a bit of a beast to work with. Why are we working with them? From a robotics point of view, as I mentioned at the beginning of this course, we could just throw away physics engines altogether and just evolve physical robots right here in the real world. Expensive, takes a long time, and I don't want to be the volunteer that goes near a robot that's partly evolved. Not maybe a fun thing to do. We're spending a lot of time in this course in evolutionary robotics, allowing evolution to try out ideas in a safe space, a physics engine. And once it proves to us that it thinks it's got a pretty good idea, we might go to the extra time and effort to build a physical version of what it dreams up in a physics engine. That's why we're agreeing to spend time wrestling with physics engines. Okay. Where did they come from? Well, they came, not surprisingly, from the computer graphics community. In the late 20th century, if you wanted to create pretty pictures in a computer, what did you do? Why does this say 111? This should say 123. In step one, you dream up your pretty picture and you write down or manually derive or compute on a calculator the position, orientation, and shape of all the objects in your scene. You type them in or describe them to a computer through a CAD program, and then you click render, and usually you'd go and get a cup of coffee, and 5 minutes or an hour later, it would render a single image for you. Okay, great, you've got your pretty picture, but you don't actually want a pretty picture, you want to create an animation or a video. So now you got to think up for all the objects in the scene, how do those objects change from time step t to time step t plus 1. You manually figure out, or with the help of a CAD program, you figure out new positions, orientations, and shapes, put them into the computer, click render, and go get another cup of coffee. Extremely time-intensive work. So in the year 2000, this brand new type of computer program or piece of software was introduced. There's our 1, 2, 3s, called physical simulation, which actually had the same goal, which was just to allow you to produce a video of your choosing, of a bunch of objects in a scene moving and changing over time. Similar flow, but not the same. You still start by defining the positions and orientations and shape of all your objects. But you would also define some additional properties of each object, which are the physical properties, the mass and friction of the object. Is it a heavy or light object? Is it a sphere of smooth ice? Or is it a sphere covered in rough sandpaper? That's the friction properties. You would define how the objects are attached together. You didn't have to do this over here because you were responsible for computing how the objects moved. Over here, you're not going to. So we need to define how the objects are attached together, because attached objects, when one of those objects moves, thanks to physics, it's going to affect the motion of the other attached object. You obviously are doing that in PyBullet by defining links and joints. And then once you're done all that, you click Start, and you as the human are done, and the physics engine, in theory, does everything else. It starts to compute the new positions and orientations of all of the objects in the scene. How do all physics do this? They're all simulating the laws of Newtonian mechanics somewhere under the hood. The simplest and the thing that they all share in common is F equals ma. Hopefully you all remember this from high school physics. Force equals mass times acceleration. Okay. First thing that a physics engine does is rearrange this equation, F equals ma, into A equals F divided by m, by dividing both sides of this equation by m. The physics engine now knows, thanks to all the information you gave it, it knows the masses of all the objects. And inside the physics engine, it's going to now go through at every time step and compute the forces that are acting on all the objects. That's something the physics engine does that you don't have to do. If you have placed an object at this height above the ground, the physics engine knows that it's got to apply a particular force to this object, which is the force of gravity, right? So there is one and only one force acting on this one and only one object in this very simple simulation we've created, which is the force of gravity. Acting on this object, we know this object's mass, so we know the acceleration of this object, thanks to F equals ma. The last step the physics engine does is to take acceleration, and it knows how much time elapses between t and t plus 1. This is something you can alter in a physics engine. At the moment, you're not doing so, but you can dictate how much time flows between each pair of neighboring time steps. The physics engine knows how much time is going to elapse. It's got acceleration. It can use those two facts to compute the new position of the object. Yeah? And in my little cartoon here, it accelerates down and then stops when it comes into contact with the ground. How does the physics engine know to stop the acceleration of the object at that point? The ground does something. Physics engines, all they know to do is add or remove forces to objects at each time step. The simplest way to stop this thing from moving when it comes into contact with the ground is for the ground to apply an opposing force, and the magnitude of that force is what? What magnitude of that force will cause this object to suddenly obtain an acceleration of 0? The opposite to the force that's pulling down on it, which is gravity. Right? So the physics engine is calculating all of these forces for you. You don't see any of this. It's pretty simple, but it gets pretty complicated pretty quickly. Okay. So as I mentioned, this new technology, physical simulation, was introduced in about the year 2000. So what we're going to do in lecture 6 here is we're going to actually look at a few code snippets. And deliberately, these are not code snippets taken from PyBullet. These are taken from Open Dynamics Engine, or ODE. This is another physics engine that we used to use in this class, but it's in C. How many of you can code in C? Oh, more hands than I thought. Okay, great. The reason we switched from ODE to PyBullet is because it's in Python, and most of you are probably more comfortable coding in Python than C. Those of you that are particularly interested in physics engines and want to get in and play around in the engine room of those physics engines, I recommend Open Dynamics Engine. Okay, so ODE, similarly to PyBullet, when things start up, you need to tell the physics engine some stuff before it even starts running your simulation. The first thing we do in ODE is create a world, and that world contains all the objects, similarly to PyBullet, in which there's something that contains all of the links that make up your robot and its environment, but that data structure is hidden from you in PyBullet. We also usually need to create something that tells the physics engine all of the objects that cannot interpenetrate. Like, for example, this object and this object, which is the floor. These two things cannot pass through one another. We'll see in a moment that there are objects that can interpenetrate or pass through one another, and we'll see why in a moment. We also need to tell ODE, and again, we do something similar for PyBullet. We need to tell it or give it some way of accounting for all of the objects that are in contact with one another, like, for example, this object and this object. It needs to know they're in contact so that it can do what? Have them react against one another. If they're in contact, like this object and this object, and they're not supposed to interpenetrate each other, any physics engine can try and obey that by applying forces to keep that from happening. That's the only currency that physics engines operate in, forces. All of the physically realistic stuff you see occurring in a physics engine and the not so physically realistic stuff you see is a result of the physics engine correctly applying forces to the objects or incorrectly applying forces. Okay. We need to tell it what is the force of gravity in this simulation. This is usually, for most folks, minus 9.8 meters per second squared, because you're interested in our case, evolving a robot to operate on this planet. NASA builds lots of physics engines in which they do not set this constant to minus 9.8. You can create other kinds of environments other than terrestrial environments in a physics engine. Okay, in ODE, this is exposed. In PyBullet, this is hidden from you, which is setting parameters that have to do with friction. Two balls of smooth ice that come into contact with one another, they apply different forces to each other compared to two balls that come into contact with one another that are wrapped in rough sandpaper. Yeah? Okay, again, optional reading, but if you're interested, this was pulled out of the actual ODE code. You can go and have a look. Okay, I don't expect you to memorize or remember the details of the code. We're just sort of seeing the necessary components we need to build into a physics engine for it to work well. Okay, sticking with ODE for a moment, and you've already done this now in assignment 2, you can create a bunch of objects or links, and we need to define some properties of those objects. In this case, we're creating not a sphere, but we're creating a rectangular solid or a box. We need to tell it the mass distribution within the box. Maybe you're creating an empty box, and inside that box are some other objects so that the mass distribution inside that box is not uniform. We're not doing that in this class. When you have a robot that's made up of a bunch of parts, if you look at any one of those parts, that part does not have a uniform mass distribution. There's a heavy battery here, or there's a heavy motor over here. We're going to skip over that detail and you're going to assume that all of the links that you create in PyBullet have a uniform mass distribution. You can roll that back if you want. You define the overall mass of the object, and then you need to set the position of the object. And that's how we do this in Open Dynamics Engine. There are some parameters that are missing. What are they? We've defined the mass properties of the object. We've defined where it starts in the simulation. Sorry, this shouldn't be a circle. It should be a box. What are we missing?
How big it is?
How big it is, its shape, and we're missing one other thing. This code suggests we want to create a box that begins hanging 6 meters above the floor. What else do you need to tell someone or something that's going to simulate a box initially placed above the ground? The floor, yeah, that's true. We haven't defined the floor here. Good point. What haven't we defined about the box itself?
I was going to say the weight, that's on line 8.
That's on line 8, yep. Not the weight, but the mass. The weight comes from the mass and the fact that we've defined gravity. In the back there, did you have an idea?
I was going to say the strength of the force of gravity.
We've set that, assume that we've set that here. We've done all the preliminaries. Now we've started to tell it, in our simulation, we want a box starting 6 meters over the floor.
We haven't defined any initial velocity.
We haven't defined any initial velocity. Good point. Usually it's assumed that velocity and acceleration start at 0. You actually don't have to assume that in PyBullet, but again, this is part of what PyroSim does, is hide a lot of these additional details. There's one important one that we're still missing. We've got mass, position, someone said size, so we're still missing length, width, and height, and the orientation, right? The box doesn't necessarily have to start like this. It could start like this. It could start like this. We're missing orientation. In ODE, these parameters are set in a different place. This seems very confusing, but there's a good reason for it. We're defining the position and mass properties of the object here. We were missing orientation. We're going to set orientation in a moment. Orientation, setting the orientation of an object is a little tricky in 3 dimensions. The usual way this is done in ODE, and you can do this in PyBullet, is to use quaternions. Quaternions, briefly speaking, are defined with 4 numbers. I want you to assume we have this particular, actually this is a better representation. We've got this particular rectangular solid that we're trying to place 6 meters above the ground plane, and we want to set it to this orientation. How do we tell the physics engine that? The way that you do it with quaternions is you define a vector that sits in 3-dimensional space, so we need 3 numbers, x, y, and z, and we're basically telling the physics engine, start by placing the long axis of this object along that 3-dimensional axis. A rectangular solid has a long axis. A cylinder has a long axis. A sphere does not. In the case of a sphere, it doesn't really matter. The 3D orientation of a sphere doesn't matter. You get the same thing no matter how you start its orientation. Okay, so 3 of the 4 numbers in the quaternion tell us how to place the object, and then the last one, theta, tells the physics engine how to rotate that object about its long axis, about this vector, and we're done. Those 4 numbers give us an orientation. Question?
So is the axis itself sort of like arbitrary?
The axis is arbitrary, right? So I define the length, width, and height of this object, which I haven't done yet in code, but when I do, I define it. One of those 3 numbers is bigger than the other, unless it's a cube, in which case, again, it doesn't matter. The physics engine is going to take the longest of those 3 numbers and lie the object along that vector, and then rotate it. For our purposes, what's sufficient here is we need these 4 numbers if you want to orientate an object in 3-dimensional space. Now, once it starts falling and hits the ground, its orientation in space is going to start to change, and it's super complicated to calculate all that by hand. This is why physics engines were invented. You don't have to. Okay. If we have a cylinder, and we do the same thing, we give 3 numbers and say, align that object or lie that object along that 3D vector. We don't need the 4th number, right? We don't need theta because a cylinder is rotationally symmetric about its long axis. Okay. Quaternions are a little tricky to work with. So again, this is all hidden from you. If you want to create a 4-legged robot in your simulation that looks something like this object, we don't need to set the orientation. It'll just by default be upright. So you've been creating links in your physics engine. The physics engine tries to make things easy on you. If you don't define an orientation, it assumes upright. Yeah. Or more strictly speaking, it creates a vertical axis and does not rotate your object about that vertical axis at all. That's the default. Okay. If we do this though, we've got this object here, which if you want to set its orientation, you can skip ahead to module P in the subreddit and learn how to do that, or you can just create a simpler robot. Things get a lot easier when we do things like this. We'll get to that eventually. Okay. Any questions about any of that? Okay. All right. Again, we're still missing a couple parameters that we need to define for this object. We'll come back to that. Joints are more or less the same in ODE and PyBullet. There are different kinds of joints that you can create in a physics engine. So far, you have been creating the most common kind, which is the hinge joint, which is very much like your elbow joint or your knee joint. We'll come back to the different kinds of joints in a moment. When we're defining a joint, what else do we need to tell the physics engine? Well, obviously, we need to tell it what two objects are jointed together by that joint. We need to also define the anchor or the fulcrum. What is this?
I think the fulcrum is, and I'm not an engineer, so it's been a long time.
It's all right.
But it's the point where the two kind of more solid pieces connect.
Where they connect. Which seems odd because you're already defining the geometric and physical properties of the two things that are being connected. So the physics engine can see where they're connected. What's the problem? Why do we need to also tell it that the fulcrum is here? This is kind of irrelevant, sort of redundant information in the hinge joint, but we can also create a piston in a physics engine, in which case it's not so obvious where the fulcrum should be. So most physics engines say, listen, just tell me, where is the fulcrum? Where is the point at which the objects move relative to one another? In a hinge joint, the two objects rotate relative to one another, but they do not move linearly relative to one another. Thank God. I'm glad that my lower arm doesn't move away from my upper arm. Rotational joints, as the name implies, or hinge joints, they're synonymous. They cause the objects to rotate relative to one another, but not move relative to one another. Question?
Yeah, you mentioned pistons. With the pistons, does the hinge or the anchor, the fulcrum move with it?
Good point. Think about it, right? So in an actual piston, you usually have a hollow tube, and then you have a cylinder moving in it, and usually there's some point of contact between this piece and this piece. It's usually the ring at the end of this piece that touches the inner surface of the hollow tube. That's the fulcrum. And yes, that position moves in a piston. So if you simulate a piston, when you start the piston at T0, you might define the piston to start like this, or you might define it to start like this, or start like this. You need to tell it, where is the fulcrum? Where does the physics engine start to apply force? So far, so good? Question?
When would the location of the hinge and the fulcrum differ?
When would the what? Say that again?
The location of the hinge and the fulcrum differ.
When would the location of the hinge and the fulcrum differ? In ODE, they never do because they're defined at the same place. So you'll notice that in these 4 lines of code, there's only one line here that kind of says where the joint is. It's also where the fulcrum is. So you're right, it doesn't usually make sense. There are a few very rare edge cases where the location of the joint and the location of the fulcrum are different. But for our purposes, let's assume in the physics engine, they're always in the same place. So far, so good? Okay. All right, so we're almost done defining our joint, but there's one additional detail we need to define, which again, in PyBullet is hidden from you. We're going to talk about this additional detail. For most of you in your final project, you are going to need this additional detail. Not yet. So you can find it in actually assignment 10. You'll get to it. It's the axis or the normal of the joint. Okay, so I'm going to use my elbow as the exemplary hinge joint here. In my cartoon here, assume this object is my lower arm and this object is my upper arm. And the fulcrum and the location of the joint is at 0, 0, 0. Yeah? Okay. Now, if I define this object, or these two objects and this single joint in a physics engine, and I turn on the physics, this object might start to fall towards the ground. And as it does, because there's a joint here, the orientation of these two objects, their rotation relative to one another, is going to start to change. This is one way in which they might start to change, but it's not the only way. Alternatively, it could start like this, and as this object starts to fall, these objects rotate relative to one another in this way. So by the time the physics engine finishes reading line 3, this particular hinge joint is underdefined. The physics engine says, do you want it to operate like this, or do you want it to operate like this, or like this? There's a lot of different ways in which the two connected objects can rotate relative to one another. So we need to define the axis about which the two objects rotate relative to one another. There's different ways that physics engines do this. In ODE, what do? You define a 3D vector which represents the axis. And in my cartoon example over here, we're defining the joint axis to be x equals 0, y equals 1, and z equals 0. The second coordinate is the vertical axis in ODE. I don't remember if that's also true in PyBullet. Doesn't matter. Okay, so my thick black arrow here, this is the joint axis, and it's pointing upward. It's sometimes called the axis or the normal for the following reason. By defining a 3D vector, again, I guess this is still high school math here, there is one and only one 2D plane that is normal to a 3D vector in three-dimensional space. So it's a little odd, but by defining this 3D vector, you're indirectly defining a two-dimensional plane. If the 3D vector is a vertical vector, the 2D plane that's normal to the 3D vertical vector is the horizontal plane. So far, so good? Okay, hopefully at this point you can see where we're going with this. This means that at t0, when the physics engine is turned on, it should assume that the rotation of these two objects are relative to one another and they sweep through the horizontal plane. As the physics starts to be integrated, F equals A takes over, and this thing starts to fall, and it gets hit by some other object. The plane, the 2D plane through which these two objects rotate relative to one another, it's not going to stay the horizontal vector, but the physics engine says, don't worry, I've got enough, I can take it from here. Yeah? Okay. In my example here, I can't draw in 3D very well. This is showing this moving like this. Okay, let's assume the exact same setup, two objects, one joint, but now I define the axis to be this way. It's pointing towards you all. How are these two objects going to rotate relative to one another once the physics engine starts running? I need an answer. My arm's getting tired. We've got a joint normal pointing this way.
Just bring your arm down by your side.
We've got a 3D vector pointing towards you this way. The 2D plane that's normal to it is this, so it's this action. Yeah? Okay. For the physics engine, that's enough. It can now simulate this joint. Again, there's some additional details that are missing. There's some other information we could give to the physics engine that might make your physics engine more realistic, or it's additional detail that you think is important to simulate this whole thing. What features of the joint is missing? What feature of your elbow joints and your knee joints are missing?
Range of motion.
Range of motion, right? My elbow will go here and then it will stop. It won't go any further. Again, thank goodness, right? So for a lot of simulations, especially when we're dealing with robots, you place additional constraints on what the joint can do. And actually, this is a very good way to think about joints in general. They restrict relative motion of the pairs of objects that they connect. If we have two objects that are not connected by a joint, they can move independently of each other in all different ways. Different joints constrain the kinds of relative motion between objects. Yeah? Okay, we're going to see lots of hinge joints and pistons in this class. What about your shoulder joint? It's not a hinge joint. It's not a piston. It's a ball and socket. The name of that joint is meant to give you a sense of how it works. How does a ball and socket joint restrict the motion of the two objects that it connects together? What does your shoulder allow your arm to do relative to your torso? And what does it not? What does it restrict? What does it not allow? Some of you are showing me, which is good. It's a good start, but we'd like to do better than that, right? We'd like to move to words and then to math. In robotics and in mechanical engineering, we talk a lot about degrees of freedom. What is a degree of freedom? Well, let's go back to the simpler hinge joint for a moment. In a hinge joint, there is 1 degree of freedom, which again, you can kind of think of as the 2D plane through which these objects move. For any hinge joint, there is 1 and only 1 degree of freedom. For a piston, it's the same thing. There's 1 and only 1 way in which the relative motion of these objects can move. They can move horizontally away from one another or horizontally towards one another. That's it. That's 1 degree of freedom. What about the shoulder? Is it 1 degree of freedom? Is it a 1 degree of freedom joint? It's more. How many more? Any ideas? Well, let's see. Okay. This is possible. So we'll call this 1 degree of freedom. Sweeping through a vertical plane, or sweeping through, vertical plane, sweeping through a horizontal plane. There's 2 degrees of freedom, and then I can move my arm through those 2 degrees of freedom. Is that it? Is your shoulder joint a 2 degree of freedom object? You can also rotate about the long axis of your arm. Depending on how flexible you are, you can get to a certain range. But intuitively, you can feel it. It's less than this one and this one. So a human shoulder joint is more than 2 degrees of freedom and less than 3. It's about 2.5. We're not going to get into the math of degrees of freedom. That's not necessary for our purposes. Just trying to give you an intuition for these things. Okay, if I want to create a 4-legged robot like we see here, and each leg is made up of an upper piece and a lower piece, and I'm going to define a hinge joint here, 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 and here. We have 4 knee joints for our robot. And then I'm also going to put a hinge joint here, 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 and here. I'm going to define those as hinge joints as well. Let's do it like the spider. So we've got this one down here and this one here. Each leg of the quadruped is capable of this. I've got a 1, 2, 3, 4, 5, 6, 7, 8 degree of freedom robot. Okay. Mechanical engineers and roboticists care about that. Why do they care about? As you can imagine, the more degrees of freedom, the more ways the robot can move, the more ways the robot can move in bad ways or dangerous ways or ways that harm itself or those that are nearby. It's a very good approximation of the complexity of the machine that we're dealing with. A Bradenberg vehicle had how many degrees of freedom? All of the Bradenberg vehicles, not all of them, almost all but one of them had how many degrees of freedom? All the Bradenberg vehicles that we saw had 2 wheels. This is not a trick question. 2. 2 rotational degrees of freedom. So it's often easier to think about wheels as a separate thing from hinge joints, ball and socket joints for that matter, pistons. It's a bit of an arbitrary distinction, but we'll use some of this terminology as we move on. Okay, let's keep going. As promised, there's a couple of details in ODE that we haven't defined for our object yet, which is the actual size and shape and the orientation of the object. In Open Dynamics Engine and also in PyBullet, but again, this detail is hidden from you, whenever you define an individual link in PyBullet or an individual object in ODE, you actually need to define 2 separate data structures. There's bodies, and in ODE there's geoms. And geoms, as the name implies, is the geometry of the object. When we defined earlier the mass distribution and the position of the object, you can think of this as like a little cloud floating at this particular position. It doesn't have a size and geometry yet. It's got a bit of a distribution of mass. A geom in ODE, the geom is the skin that surrounds the object. So in a lot of physics engines, the inside of an object, the mass distribution and its position, is separated from the skin surrounding it, which seems like a weird way to do things. The reason why physics engines do this is the physics engine uses F equals ma to predict motion of the objects, generally speaking. And remember, there's the F and the M. That's the inside stuff. M for mass or mass distribution, and F for the forces acting on that mass. Has actually not much to do with the shape and size and orientation of the object. Can be a little confusing to think about. When the physics engine is using F equals ma, from its perspective, it's dealing with little localized clouds of mass. But when those little clouds of mass get close to one another, now it can't deal with clouds anymore. It's got to deal with the actual geometry of those objects, because maybe those objects are about to come into contact with one another, or they just have. And now there's a different part of the physics engine that takes over that deals with how bodies interact with each other. They're usually different parts of the house in a physics engine. That's why they're separate. Okay, so in the geom here, the last piece for this box that I was creating before, sorry, I'm jumping around too much. I'm gonna wrap that little cloud in a length 1, width 1, height 1 box. I'm putting a skin around this thing. I am not setting the orientation of the box, so we'll assume it's just sitting upright 6 meters above the world. And I take that skin and I wrap it around this body, and I'm done. In ODE, I've now completely characterized a single object, or in PyBullet, a single link. A lot of effort up front, but we recoup all of that effort once we turn on the physics engine and it does the harder stuff for us. Yeah? Okay, so we're going to spend a few minutes now talking about collision detection and resolution. These are two sub-aspects, or these are 2 aspects of dealing with or figuring out how 2 bodies interact with one another. Collision detection is actually the harder part. This is the part in which it tries to determine whether 2 things have actually come into contact with one another. Collision resolution is a little bit easier. Okay, so how does the physics engine do this? Let's start with a different cartoon example. Let's imagine that I start by dropping 1, 2, 3, 4, 5, 6, 7, 8, 9 spheres at some distance above the ground plane. So I'm creating a different physical simulation in this case. We're dealing with spheres. For spheres, collision detection is pretty easy. If I have the position and the radius of an object and a position and radius of the other object, how do I know if they're in collision or not? Not too tricky.
If the centers are within the combination of the radii.
If the two centers are at the same distance or closer than the two radii of the two objects, they're in collision, or they've passed collision and they've interpenetrated one another. Usually a no-no in a physics engine. Yeah? Okay, so I've got 9 objects. The physics engine needs to do how many collision detections? The simplest thing, I go to each of the 9, I start with this one, and I compute its distance from each of the other 8. So that's 8 calculations. Then I go to the second object and compute its distance from each of the other 8 objects. That's another 8 collision detection events. So now it's 16, 27, 36, how many in this lazy way of doing it? 72, right? So 9 times 8 equals 72. 72 collision detection events, okay? Every time step. If I drop 100 ball bearings at random above the ground plane, how many collision detection events does the physics engine need to run every time step? 100 objects.
$9,900.
Thank you. That's a lot. Every time step. When the fan turns on when you're running your physics engine, it might not yet, but once you get to assignment 10 and on your final project, it certainly will. What is your laptop wrestling with? It's actually not wrestling with F equals ma, which is easy. Go to every object and take the forces acting on each object and compute the new acceleration. For 100 objects, you need to do that F equals ma calculation 100 times. For collision detection for that same scene, you need to do 990,000 detection events every time step. That's the rate limiting step. That's the thing that eats up compute in physics engine. When you watch CGI in a superhero movie, all of the compute and all of the carbon that was spewed out in the creation of the CGI for that movie came from the superheroes colliding with one another and their axes and swords and shields colliding and all the way down. That's the rate limiting step. Okay. Super computationally expensive, costs a lot of carbon to do. Can we do better? If we have n objects, can we do better than n times n minus 1 collision detection events every time step? I see some nods. Any idea how?
Well, you don't need to compute the distance between each of them twice.
Exactly, right? So when I visited the first one and computed the distance to the second one, I don't need to, when I get to the second one, compute the distance to the first one. So how much better can I do if I don't do that? Anybody know? Yep.
N factorial.
N factorial?
I mean, it's half as many.
It's half as many. If you go through and do that, you'll see that you've computed the distance between the same pair of objects twice. Okay, so in this scene with 9 objects, we can reduce 9 times 8. Oh, I've run over time. I'm sorry. Got all excited about collision detection and resolution. You have a quiz due tonight. You have some assignments due. See you on Thursday. Apologies for running late.